Okay, so we're going to look at a vector addition problem mathematically. So we're going to find out what our resultant vector C is if I add two vectors together. What's my magnitude and my direction of resultant vector C? So the first vector, vector A, is given at 6 magnitude at 15 degrees left of the positive y-axis. And vector B is given as 8 magnitude at 15 degrees. And when we're not given information, that is always relative to the positive x-axis. Now we've been talking about how to get those angles over the course of this particular unit, and we remember that if I want the horizontal and vertical components, I can use my sort of standard cosine and sine only if I am referenced to the positive x-axis. So that'll work for vector B. Okay, so let's just start with vector B. It'll work for that, and we can move on, and then we'll look at what happens for vector A. So vector B. It's at 8, so our horizontal component is going to be 8 times the cosine of 15, and our vertical component will be 8 times the sine of 15. So 8 cosine of 15 is 7.73, and again, I'll reduce the significance later. 8 times the sine of 15 is 2.07. All right, what about vector A? Well, it's important for us to understand what this vector really looks like. So if I were to draw a coordinate system and plot vector A on that coordinate system, I would have a magnitude of 6, so I can just pick a length that represents 6, but it's left of the positive y-axis. Well, here's the positive y-axis, so 15 degrees left must look something like this, where theta here is equal to 15 degrees. Now, as we have talked, there's multiple ways that we can solve for the horizontal and vertical components of this vector. One way is to reference the positive x-axis and then use my standard. So if this were my angle alpha, alpha is equal to 90 degrees plus 15. Well, 90 plus 15 is 105 degrees. Now I have an angle relative to my positive x-axis, and I can use my cosines and sines appropriately. This is my preference. I like to reference things to the positive x-axis. In doing so, I would end up with the magnitude 6 times the cosine of 105 and 6 times the sine of 105. And when I solve for that, I get 6 cosine of 105, I get negative 1.55. And 6 sine of 105, oops, 6 sine of 105, I got two negative values there. So I plugged it in wrong, obviously, is 5.80. Now, I've given a negative out of my calculator. I expect it to be negative. This vector is pointing towards the left when I think only horizontally. And I get a positive y component. A vertical component. I see that that vector is pointing upward. So that's one way to do it. Well, I appreciate that that's not everybody's favorite way to do it. Sometimes we like to do things using the angle that we're given. So in that case, if this is the vertical component and that is the horizontal component, we certainly can use the trigonometry we're comfortable with to get the magnitude of each component, but we have to be careful about the direction. So if I'm going to use that 15 degrees, and let's start with my horizontal component. Well, this angle 15 is opposite the horizontal component. And so my relationship to get horizontal would be 6 times the sine of 105. Of 15. Times the sine of 15. And if I were to want to get the y component, that's adjacent. So 6 times the cosine of 15. Now we have to be a little bit careful. We'll see that in just a minute. So we have 6 times the sine of 15. Well, that gives me I don't know why I do my calculator, I know the answer, 1.55. But because I'm using this interior angle, I have to be attentive to that direction, and I have to be explicit about it. my horizontal component is pointing to the left. So I have to add that negative in despite what my calculator tells me, because the physics tells me it's pointing to the left. And we see these two match. 6 times the cosine of 15 is 5.80. And I also want to check, should I have a positive value? Well, that y component is indeed pointing upward. And so yes, I should have a positive value. And so it stays what the calculator gave me. All right, so keep in mind, you can do it either way, whatever you're most comfortable with. Make sure you're being careful if you use the alternative interior angle, or sorry, the interior angles, and make sure that you're paying attention to that physics. All right, so now we can just move on with the same process we've always been doing. I add my two vertical or horizontal components. I have 7.73 plus a negative 1.55, and I get 6.18 horizontally, and 2.07 plus 5.8, and I get 7.87 vertically. Now, to find the magnitude of that vector, remember we take the square root of the horizontal component squared plus the vertical component squared, and that gives me 6.18 squared plus 7.87 squared, and I end up with 6.18 squared plus 7.87 squared. Take the square root of that. 10 is my magnitude. And my angle, remember, is the inverse tangent of the y component, vertical component, over the horizontal component. And I end up with 6.18 over, whoops, that's the x, the horizontal. That's no good. 7.87 over 6.18, and I get 7.87 divided by 6.18, 51.8 degrees. Now, I have to ask myself, does that make sense? We always have to ask our angle, because remember, tangent just gives us first and fourth quadrant. So, is it in the first or the fourth quadrant? Is that number legit? Well, I have a positive horizontal and a positive vertical. That means I'm in quadrant 1. This is my answer. All right, so a couple things to just remind us. Keep in mind, thinking about what angle we're actually given and what the appropriate components are, whatever method that you've chosen to do. And then, as always, whenever we add vectors, to keep in mind that tangent idea of first and fourth quadrant and making sure that's where our vectors lie before we quote that angle. Good job.